I hope you haven't forgotten me.
Hello.
Hello. So, I had some good news that should check with Patrizia, but I think that next week we will be able to have our classes here, with you here, if I understood that correctly. I think you will get an official communication from Patrizia, but it's in the Budinich lecture hall, so there's plenty of space, and so I think you will have the option of coming here, which I think would be much nicer way to have class if you want to. I think probably it will be streamed as well, so you can choose. Okay, so there's been a big gap to kind of catch up. Are there any, I know you've had a couple of tutorials and you've looked at a bit of the exercises. Are there any comments or questions before we move on? Everything crystal clear. Good. So let me just review the fundamental result, let's say, right, that we talked about in the last couple of lectures. We introduced this ergodic theoretic way of studying dynamical systems, right? So we introduced the concept of a physical measure, the concept of invariant measure, the concept of an ergodic measure, and so if we want to summarize, really summarize just in 2 lines the main points. So if we have some set X which we assume is a manifold or something that has some Lebeg measure, something with a bit of structure so that we can talk about a reference. Lebeg measure like the unit interval or the circle or some other manifold. And if we have mu probability measure, and then if you remember, we defined the basin of mu is the set of points whose asymptotic statistics is described by this measure, right? By which we mean that we have this sequence of measures along the orbit of the initial, so x0, all the points in our space such that this converges to mu. Right? And then basically a way, this is not exactly Bilk's Sargonic theorem, but essentially one of the corollaries of Bilk's Sargonic theorem is that if mu is invariant and ergodic, and if the space X has, as I said, a kind of differential. This doesn't need a differentiable structure so far. Just if the space is, for example, a compact metric space, then we have that the basin of mu is non-empty and has full measure. Right? This is really, so the Bilkov-Sargonic theorem is a bit more general. It is a more general statement that applies to measurable maps on measure spaces, but if X is a compact metric space, then we have this corollary of Bilkov-Sargonic theorem, and as a corollary of this, we have that if Lebeg measure is, if we have, for example, the unit interval or the unit circle, Lebeg measure is involved, then if mu is invariant, ergodic, and absolutely continuous with respect to Lebeg. So this means that absolutely continuous means that a set with 0 Lebeg measure must have also zero mu measure. then this implies that, that it's a physical measure. Any questions about this? Okay, so this is really essential that you have in mind. This is, in some sense, the big picture of what we did. You know, we did quite a few more details. We didn't do the proof of Birkhoff-Sargonic theorem. We did the precise statement. There's some additional results like the Poincare recurrence theorem that are important to know. But this really is the core of the results that we arrived at, right? That we are looking for physical measures. So we're looking for measures for which this basin has positive Lebeg measure. And this is one set of conditions that guarantee this. This is not the only set of conditions. There's many other ways that you can have physical measures. Some trivial ones, if you have a contraction mapping, as we saw, then you have a fixed point, everything converges to the fixed point, and then the Dirac delta on the fixed point is a physical measure also, right? And then there's some more complicated measures called Sinai-Ruel-Bowen measures that are kind of in between the contraction and the absolute continuity, but that's geometrically quite a bit more complicated, and we will not be able to do it, to treat them in this course. But the absolutely continuous case, there's a lot of interesting dynamical systems in which we have exactly this situation, and these are the ones we're going to study in these remaining 3 courses. And as I said before, one of the biggest challenges this is a kind of roadmap, right? This is a kind of suggest a strategy. It's not necessarily the only strategy, but if we're looking for physical measures and we have this corollary, then it's a natural strategy to say, okay, let's take a system and try to find out if it has an invariant, ergodic, absolutely continuous measure. So the most difficult in general, in many cases, the most difficult part is the ergodicity part. The existence of invariant measures is very general. We proved some theorems that in many general situations you have invariant measures. So the difficulty is the ergodicity and the absolute continuity in general. But in some cases, the absolute continuity is automatic. So for example, we already showed that if f on the interval is a piecewise affine full branch map, then the Lebeg measure is invariant. Right? This was one of the exercises that I gave at some point. It's very important that you do this exercise if you've not done it, just to get a feeling. This is true even if it has an infinite, even if it has an infinite number of branches, right? Lebeg measure is invariant. So, but of course, the simplest cases are just cases like 2x mod 1. Right, so if we have, for example, 2x mod 1, then it's very easy to see that Lebeg measure is invariant. So if Lebeg measure is invariant, then we have already verified 2 out of 3 of these conditions, right? Because Lebeg measure is invariant. Lebeg measure is trivially absolutely continuous with respect to Lebeg. It's all of Lebeg measure. So if we can show that this map, that Lebeg measure is ergodic in this case, then we will have, in fact, that since we are looking at Lebeg measures, the invariant ergodic measure, mu is Lebeg measure, so we get automatically from here that the Lebeg measure of the basin of Lebeg is 1, so it's got full measure. So almost every point here is distributed according to the statistics of Lebeg measure, right? So this is one of the consequences, if you remember, of Bilk of Sargonic theorem, which is also included here, is that the statistics of orbit, the frequency of orbit, so if you take, so here we're looking at the interval 0, 1, so if we take any interval here, A, okay, if almost every point is in the basin of Lebeg measure, then it means that asymptotically the orbit is distributed according to Lebeg measure. So if you take any set and you measure the frequency of visits to this set, it will converge exactly to the Lebeg measure of the set. That's one of the consequences of Lebeg measure itself being invariant and ergodic. Even though, of course, as we know, there's many points that don't satisfy this, right? For example, there's the fixed points, there's periodic orbits. If we take a point, a set here, there may be a periodic orbit that never visits the set A, right? Because the statement is that the basin has full measure, not that every point satisfies this kind of distribution, right? That typical point, so Lebeg, almost every point satisfies that. So today we're going to prove the ergodicity, and then also some, if we have time, some interesting applications. Okay, so today we're going to prove theorem is that if F is piecewise affine full branch, Lebeg measure is invariant, okay, and ergodic. So in this case, it will be quite easy to prove ergodicity, but it will be an interesting exercise to do that, and it will start giving a feeling for the kind of things we want to show. So I'm actually going to, as you know, I don't do many proofs in this course, but I think this proof is interesting, and we will go through it. So, so the proof uses the structure of full branch maps. So if you remember, I think that we discussed the general fact that every iterate of a full branch map is a full branch map, right? So you can keep this in mind, but if in general, if F is a full branch map, then Fn is also a full branch map. With partition, with some partition Pn, right? So we have, in this case, it's just n, but we don't, on the one hand, we want to use this as a model, but on the other hand, the result is general. And here we have that if you take some omega, some element omega n in Pn, right, then Fn maps omega to the interior of this whole interval I. These are all open sets, right? So this is a bijection, and in fact, in this case, it's affine. Okay, and in this particular case, so we do use the fact that it's piecewise affine, then it's clear that the derivative is larger than 1, is bigger than 1 everywhere, right from the beginning. So this is a piecewise expanding map, and therefore it's easy to see, I think I gave this as an exercise, is that the supremum of the sizes of these omega n's with omega n in Pn goes to 0. This is the Lebeg measure, the size of the interval. This goes to 0 as n goes to infinity. So of course, this is intuitively obvious, but unless you have the expansion, is not necessarily true. So you have this sequence of partitions, smaller and smaller partition elements. So here you will have a partition with lots of intervals, and each one will be mapped a piecewise affine way to the whole thing, right? They don't have to be, sorry, maybe let me clarify that. Of course, they don't have to be all the same size, right? Because I'm not assuming that they all have the same size, but you get, and also I don't assume I'm drawing them with the same orientation, but that is not necessary either, okay? And then here you have this partition Pn, and you have these elements. Okay, so now how do we prove ergodicity? So this is the structural information, the basic information we have about full branch maps. Now, how do we prove ergodicity? So remember the definition of ergodicity. So we need to choose a set. Let A be a set that is backward invariant. Okay, so I also gave a few exercises for you to develop an intuition. This is not a completely, for non-invertible maps, this is not a completely obvious concept, okay? Because if you take some point, it will have several pre-images. You need to take all the pre-images and all the pre-images. But then if you want f minus a of a to be equal to a, then you also have to take the images and the pre-images of the images, right? So if a set satisfies this condition, I think maybe I discussed a little bit of this, then it really is a set that is very invariant, strongly invariant. All the images and pre-images and pre-image of the image, they all belong to this set. So it's not so easy. Of course, the whole interval satisfies this condition. If you take a point, you can easily construct a countable set that satisfies this by taking exactly that. You take the full orbit, forward orbit, and then you take all the pre-images of all the points of the orbit, and you get a set like that. But that is just a countable set, of course, right? So if you remember, ergodicity says that indeed that's what the situation is. That if you take a set, either it is everything, or at least it has full measure, or it has zero measure, right? It's indecomposable in that sense. So we're going to assume that it has positive measure. So suppose that Lebeg measure of A is positive, and then we will prove that it has full measure. Right? This implies ergodicity. This is ergodicity, right? Because it says that A can only have either zero or full measure. So if we assume it's got positive measure, we prove it must have full measure. So those are the only two options. So fortunately, we do not need to analyze in detail all the possible kind of sets of this kind. It's a fairly abstract argument that we have here. And it uses a very remarkable result. So we need a result called that some of you, I'm sure, will know. We need the so-called Lebeg density theorem. So let me state the Lebeg density theorem. The Lebeg density theorem says the following, that if you have a set of positive measure, so here we have some set A that has positive measure, right? I'm not going to draw it, but because it may be a very strange set, I'm not assuming that this set is an interval or anything, right? So we have some set A that has positive measure. And now the question that the Lebeg density theorem addresses is, how is this measure distributed interval at different scales, right? So suppose that the measure of A is 1/2, for example. So this means that at the scale of the interval, half of the measure belongs to A. Okay, so I can ask, is it possible to take this measure and distribute it really uniformly in such a way that any interval I take, half the measure of that interval will belong to A? So if half of this measure belongs to A, then I can say, okay, let me take an interval here, and maybe half of the measure of this interval belongs to A. Right? Is it possible that any interval I take, half of the measure belongs to A? And the Lebeg density theorem says that this is not how it works. Okay? The Lebeg density theorem says that if you go to very small scale, either you belong to A or you belong to the complement of A, basically, in measure. Okay, so the Lebeg density theorem is really a remarkable theorem. What do we mean by that? So the formal statement is like this, is for almost every x in A, we have the following, that if you take the measure of some neighborhood, epsilon neighborhood, so you take the measure of the interval x minus epsilon and x plus epsilon, right? So you take some point here, you suppose this point belongs to A, right? And then you take this little neighbor, so this is the point x, this is x minus epsilon, x plus epsilon, okay? And you take the measure of this intersection A, right? So you look at this little interval, and you look at how much of A. So this point here belongs to A, so there might be some measure of A inside here. And then you divide by the measure of this interval, by the Lebeg measure of this interval, which is just 2 epsilon. So what this is saying, this is the proportion of this interval that belongs to A, right? Because here you have the Lebeg measure of this interval on the denominator, and on the numerator you have the Lebeg measure of A restricted to this interval, right? So if, for example, half of this interval A belongs to A, then this would be equal to 1/2, this ratio, right? And what Lebeg density theorem says remarkably is that the limit as epsilon tends to 0, this is actually equal to 1.
Otherwise, it's 0. If x does belong to A, then it's 0, the limit. If x outside the A.
Exactly, exactly, because you can apply to the complement in the same way, right? Yes, exactly. So what this is saying, yes, that's right. That's a good observation, Mimukhin. In terms of the philosophy that I was saying before, it's like for almost every point, sufficiently small neighborhood, either 90% in A or 99% in A or 99% outside A. You kind of have a choice there, right? So at very small scale, the measure, in principle, you could imagine, why not? You know, if the total measure is 1/2, maybe this, at every scale, you have that kind of relative proportion, but this is not the case. Okay, sorry, this was a little diversion in measure theory. Maybe you're familiar, but maybe if you're familiar, maybe you've not thought about it exactly like this, so I just thought I'd spend a few minutes on this. And why is this important? Because we're going to apply this to our set that has positive measure, right? And we're going to, so you can see actually, okay, I stated this Lebeg density theorem for a symmetric interval, but you can intuitively see that you don't really need to take such a symmetric interval, right? If you take a small interval, a small neighborhood of x, and you divide by the size of the interval, then as this size goes to 0, you will get the same result. And we're going to focus in, so we're going to choose a point. So these are called the points. This is for almost every x in A. So these points are called Lebeg density points of A, right? So if a point satisfies, this is not for every A, but for almost every. So a way to state this is that almost every point is a Lebeg density point of A, right? So now we have our set of positive measure, and we're going to take a Lebeg density point of the set, right? So suppose that this point here is a Lebeg density point. So once we take a Lebeg density point, then we know that in a neighborhood of this, 99% of the measure belongs to A, right? So now we can use this result here that says that if you take very large n, you are partitioning this interval into very small elements, right? The elements omega n, they're very small. So clearly, we can find some n. So there must exist n sufficiently large and some omega n in Pn, okay, such that if you just look at omega n intersection A, so we look at omega n intersection A, and you divide this, so you take the Lebeg measure of omega n intersection A over the Lebeg measure of omega n, then this is greater than or equal to 1 minus epsilon. Right? So for all epsilon, so maybe I should write, for all epsilon, I can find n sufficiently large, because when n is sufficiently large, these are very, very small, right? And so I'm getting finer and finer partition on the interval, so I'm squeezing around this Lebeg density point. I choose some Lebeg density point, and I take the interval that contains this Lebeg density point, and then when this interval is small enough, I will get that the measure of A inside omega n is arbitrarily close to 1. Okay? And what this means is, in fact, that it will be a little bit more useful for me to say that the Lebeg measure, of course, this implies that the Lebeg measure of omega n intersection the complement of A over the Lebeg measure of omega n is less than or equal to epsilon, of course, right? So if inside omega n you have at least 1 minus epsilon measure that belongs to A, then there must be less than epsilon measure that belongs to the complement of A. And now the way and this implies, so now I have, this is omega n, and omega n by Fn maps to the whole interval. Wait, sorry, let me draw it a little bit here. So omega n by Fn maps to the whole interval I. This is the interior of I, Fn. And this map here is affine, right? Because we have a affine map here. So that means that here we have, inside here we have omega n intersection A complement, right? And so here we have, somewhere inside here, we have the image of omega n intersection A complement. Right? Just the image of this subset. This is a subset of omega n, is the complement of A intersection omega n. We take the image, and because Fn is affine, so Fn is affine, then it preserves the ratio between the measures, right? It's affine, so it stretches everything uniformly. So it means that the ratio between this and this, the ratio between omega n, this ratio here, is exactly equal to the ratio between the images. So here we take the Lebeg of the image of omega n intersection AC, and here we take the image of Fn of omega n. Right? But of course, Fn of omega n is just the whole interval here. Right? So it has length 1. The Lebeg measure of this is 1. So this is just equal to this. Lebeg measure of Fn of omega n intersection AC. Okay. So our conclusion, this is completely formal. We've used the fact here that we have an affine map, and we conclude that this is less than or equal to epsilon. And now the last step is just a small observation. What does this mean? So it turns out this is a small kind of technical calculation. I think I will leave it to you to look at the notes as to why it's true. But it turns out that here, if you look at, so the complement of A is backward. Well, maybe I will write it. Might as well write it. So remember that F minus 1 of A equals A implies that F minus 1 of the complement of A equals the complement of A. I remember we made that observation that AC is backward invariant. And this implies that, of course, F minus N of AC is also invariant AC. And this implies, therefore, that Fn of omega n intersection AC is equal to Fn of omega n intersection F minus n of AC, right? Because these AC is equal to F minus n of AC. And this is just then, you can kind of take the intersection of the images. This is the same as Fn of omega n, intersection Fn of F minus n of AC, which is just equal to AC. And this Fn of omega n is the whole interval 0, 1. So this is just equal to AC. Okay, so you should, of course, check this little calculation. This is just set theory. There's no particular argument. But what this means is that this implies that AC, that the Lebeg measure of AC is less than or equal to epsilon. Which completes the proof, right? Because we have shown that for every epsilon, the Lebeg measure of AC is less than or equal to epsilon. Okay? So this means that Lebeg measure of AC is equal to 0. So this completes the proof of the fact that the Lebeg measure is ergodic. As you can see, it's a very simple proof, but it contains a couple of key points which I just want to make a remark for future, because we, as mathematicians, we always want to look to possible generalizations, right? So we've used here the fact that it is piecewise affine, right? We have seen, of course, that in several situations we want to really generalize from piecewise affine at least to piecewise C1, uniformly expanding. So where did we use in this proof the fact that it is affine? Can you see where we used in this proof?
In the last step, just there is some proportion, like stretch at the same level.
So we have used it. First, we have used it in a very weak way. We've used it.
Omega n goes to 0.
Yes, exactly. We've used it here, but we already know that we can replace this by uniformly expanding C1, and we still get this, right? So this part is easy to generalize. If it is C1 uniformly expanding, then this goes to 0. Then we can choose. We get this. We get up to here. This does not need really piecewise affine. We can immediately generalize it. But here, as you correctly say, Mokshin, here, for this equality, this equality is based on the fact that we are iterating Fn. We're iterating this set here and this set here, right? And that these proportions are preserved. So clearly this is not going to be true if it's not affine.
Maybe we change some equality. Maybe we, after some generalization, maybe we can get only inequality, because inequality is also enough for us.
Exactly. That's exactly the observation. We're going to do that next week. We're going to generalize this result. And here, as you can see, what we need is just to show that this is going to be less than equal to epsilon. We don't need an equality, right? We need an inequality. We just need to show that this is less than or equal to even some constant times this, as long as the constant does not depend on n, right? So that's correctly. So I just wanted to point this out. Here we use affine, but this is not necessary, right? An inequality is sufficient here. Okay, so we have the ergodicity. Very good. So for the rest of this class, I want to really just give a couple of what I think are very interesting applications of this result. There are two applications, there are related applications. So the first one is the following. So application to number theory. There are lots of applications of ergodic theory to number theory. I don't actually know, I've never worked in this, but I think it's really interesting. There's a lot of people, a lot of very senior researchers who work on number theory using methods from ergodic theory, and I think this is the first simplest. This application is very simple, but it's a very nice example of the way ergodic theory can include for number theory. So remember that if we have the base k expansion, right? So we can, for integers, we already discussed this when we were looking at kx mod 1. For integers k greater than or equal to 2, we can write numbers, we can write real numbers in a base k, right? So we write x equals 0 point. This is the expansion. So this is the expansion. We have xi belongs to either 0, 1 to k minus 1. So if k is equal to 10, then we have the decimal expansion, right? So we get all the digits between 0 and 9. We get all the possible combinations, right? If k is equal to 2, this is the binary expansion, base 2, just zeros or ones, okay? And we have all these possible sequences, and then we write a definition. We say that x is normal in base k if it's a base k expansion, if its expansion in base k contains equal proportions of each digit. Right, so I will write in a second the formal. So for example, in base 10, in the decimal representation, we say that a number is normal if the frequency of each digit, zeros, ones, twos, is 1/10, right? Each of the 10 digits appears 1/10 of the time in its expansion, asymptotically, right? So this means that we have that if we take 1 over n and we count the number of digits between 1 and n such that xi is equal to k, not k, is equal to j. So for all j amongst the allowed digits, the proportion, like this is, you look at this and you look at the limit as n tends to infinity, and this is exactly equal to 1 over k. Is that clear, the definition? So asymptotically, it has the same proportion of all the digits. So this is a definition that makes sense. A number, you take a number, it may or may not be normal. Clearly, it's easy to construct normal numbers. For example, if I just take 0, well, periodic orbit 0, 1, 2 up to 9, and then 0 up to 9. Okay, so this decimal expansion is repeating, and it obviously contains 1/10. You can also construct, you can see that you can have non-periodic points that have the same property. So I think you should be able to see immediately what we're going to say about normal numbers. That it's a quite easy corollary of our result theorem. For all k greater than, so for every integer k greater than or equal to 2, Lebeg, almost every x is normal. And why is that? Bahama, how about giving us some ideas? of why this should be true. Do you have some ideas of why this might be true? How we can do this? Ling, you have some idea? How is this related to what we've just proved?
Lebeg density.
You develop that? So how do we relate, what does this have to do with dynamics, right? So I'm mentioning, this is a purely number theoretic statement, right? At least I stated it on purpose like that. This is nothing to do with any dynamics, the statement, right? This is just looking at numbers, base K representation, and we want to claim it's clear that not every number is normal, right? This is obvious. So we want to show that almost every number is normal. How can we relate it to some dynamical system that we know? Ruba, you have some idea? Is anybody there? Toluwani, what do you think?
Maybe KX mod 1.
I couldn't hear you.
Oh, I said KX mod 1.
Yes, try to speak a little bit louder, please. So KX mod,
Okay.
KX mod 1, you want to look at the map f of x equals kx mod 1. And what are we going to do with this map? Why is that? How is this going to tell us anything about the normal numbers?
The orbit is just digits, namely.
Okay,
if
wait,
it's
Mokshin, wait. Let's give other people a chance. Can you develop that? You don't need to give the full answer from the beginning, but why is this related to the base K expansion? How is this map related to the base K expansion? What about Junaid? Junaid, can you tell us?
No idea at the moment.
No idea. What about Eunice? Eunice there?
No, I don't know.
You don't know. Whoa. I guess we left too much time here. We let pass too much time and you got lost on the other courses. I let you all forget what we're doing, right? Okay, Mokshin, I think you've earned your chance. Tell us.
I think just if we fix initial conditions, then the orbit is just digits of that number. Namely, the first digit is first iteration, second digit.
Exactly.
Second iteration.
Exactly, right? So we've seen this. I'm sure we've seen this before. So if you have the map fx kx mod 1, then this map is a k branch map, right? So let's just take k equals 3 for simplicity, just as an example. But you can easily do it for the other branches, right? So right? So this is 0 to 1/3, 2/3, and 1, okay? So how does the, if you remember, what is the action of f on x, fx? The action, so let me write it in words. So the action of f on x base k, okay, remember that in base k, x is written like this, x1 over k plus x2 over k squared plus x3 over k cubed, and so on, right? So this is xi belongs to 0 to k minus 1. This is what the base k expansion, right? I didn't write it, but that's what this base k expansion is, right? When k is equal to 10, this is the 10th place, the 100th place, the 1000th place, right? So this is the base k expansion. And when you take f of kx mod 1, right, then kx is equal to x1 plus x2 over k, right? You multiply everything by k, and you get x3 over k squared, and so on, x4 over k cubed, okay? And when you take mod 1, this is an integer here, right? This is either 0 or it's an integer. So when you take mod 1, you just drop this, and you get x2 over k plus x3 over k squared, and so on. Okay? So the new expansion, if you start with x whose expansion is x1, x2, x3, then this will be 0.x2, x3, x4, and so on, right? So the action of f, if you write it in base k, it's just the shift. Remember, we did it in the case of 10x mod 1, it was the first thing we did, and I thought you would know it in your sleep by now, right? When you take 10x mod 1, the effect on the decimal is just to shift it, and when you take kx mod 1, the effect on the decimal is just to shift it. And what information do you have from the first digit, okay, is of course that it tells you exactly which of these intervals you're in. So if this is an interval I0, I1, and I2, if you write something in base 3, right, and you look at the first digit here, x1 over 3, where x1 is 0 or 1 or 2, then this digit can be 0 or 1 or 2, and it tells you exactly if you're in this interval or in this interval or in this interval. Is that clear?
Yes.
Yes? So the first digit tells you exactly which of these intervals, which branch you're in, right? And then when you apply f, right, you get a new number whose base k expansion starts with x2, which means it starts with the second one. And so now this one, you look at x2, and depending on whether x2 is 0 or 1 or 2 or whatever, you know which of these three intervals the image is going to be in, right? So when you look at the base k expansion, these digits, they give you exactly the symbolic coding of this point, right? They tell you exactly the sequence of the branches that you will fall in, of these intervals of the partition. So if you want to know how many zeros there are in the base k expansion, this is exactly the same question as saying how often along the orbit of the point do you fall in I0? Because you always fall in I0 if and only if this digit is 0. right? And similarly, you fall in I1 if and only if this digit is 1, and so on. So there is a perfect correspondence between exactly the value of the digit and the interval that you fall in. Okay? So Toluwani, now that we have this, how do we complete the proof of the theorem? We want to study the proportion of zeros inside the base k expansion of x. How do we use the dynamics to do that? The proportion of zeros that we get in the base k expansion is exactly the same as the proportion of times that your orbit will visit this interval here. Right? And what is the proportion of times that the orbits will visit this interval here? If you look at the dynamics of a point, how often will it fall in here? You know? Junaid, can you tell us?
Uh, 1/3.
Why is that?
Uh,
See that you're all a bit rusty here. Huh? I've left you, I've abandoned you for too long. It's all forgotten, everything we did here. I'm a little bit disappointed, I have to confess. Ling, what do you think? Why does almost every orbit visit this interval for asymptotically 1/3 of the time?
It's Poincare recurrence. It looks like.
No. Poincare recurrence says that it will visit infinitely many times.
No, just result of Birkhoff's theorem. If we consider some interval and its characteristic function.
Exactly, right? The corollary of Birkhoff's ergodic theorem says that if a measure is invariant and ergodic,
Yes.
right?
Then the statement is the same.
Yes, if it's invariant and ergodic, then if the frequency for almost every point with respect to that measure, the visits, the proportion of time that you spend in a certain set converges to the measure of that set.
Yes.
Right? This is the fundamental corollary. Maybe I should have written that instead of, but it's basically a consequence of this. But probably I should have written that is also it's not the fundamental corollary, but it's the intuitive, it's the picture you should have in mind of what Birkhoff's ergodic theorem says, right? That the frequency of visits to a set converges to the measure of that set. So why is this an application of the theorem that we just proved? Because we need to prove that the measure is ergodic for that, right? Not only invariant. So Birkhoff's ergodic theorem needs the measure to be ergodic. We've proved that the measure is invariant and ergodic. So we've proved this implies that Lebeg, because Lebeg measures invariant and ergodic, so Lebeg almost every point visits any interval here asymptotically a proportion of times that is the measure of that interval. Okay, but what we're interested in particular is this interval here. So this interval here, almost every point will visit 1/3 of the time, or in the general case, it will visit each branch because all the branches have equal size, all the partition elements for this, 1/k times, okay, asymptotically. And if it visits here in proportion 1/k times, as we said, every time it visits here, it means that you have a 0 in the base k expansion. So that means that the 0 appears exactly with proportion 1/k. in the base K expansion. Right? So this is the simple consequence of just the fact that there is this connection between the dynamics and the decimal expansion tells you immediately what you have here. Okay, so before we have a break, let me just give one more remarkable. This is perhaps a kind of really now an immediate consequence of this is, of course, that corollary is that Lebeg, almost every x is normal in every base, every integer base. Okay, this is very easy because, of course, the proof is that just that the numbers, this is just the intersection of every k, right? So if nk is the set of full measure for which of points which are normal in base k, this is just a countable intersection, and the countable intersection of full measure sets has full measure. Okay, so this is a kind of trivial consequence. But the curious thing is that as far as I know, I don't think any number is known explicitly that is normal in every base. So this is a completely abstract result, and as far as I know, there is no number, there's no relation between the bases. If you know that a number is normal in one base, it's not obvious. I don't think there's any algorithm or any way to automatically kind of study whether that particular number is normal in another base. So there's no particular way. As far as I know, nobody knows any number in this. So I think that is that is curious. And again, anyway, this is a purely number theoretic result. But as you can see, the proof is ergodic completely, right? So I think this is interesting application of it. It gives you a feeling of a kind of results, why ergodic theory can be relevant in number theory, right? Especially when you're looking for asymptotic properties of numbers, like in this case. Okay, so let's just have a very quick break of 2 or 3 minutes. Now it's 4 minutes past, so let's just take a 3-minute break and then come back for the second application. Okay.
Professor, I believe you're muted. Check the microphone.
Hello?
Yes, works now. Thank you.
Sorry, I was talking without microphone, but maybe everyone is sleeping as they don't know, nobody noticed, possibly. So what I said was that we study the map 2x mod 1, and we want to study the class of invariant and ergodic measures here, right? So we've just proved that Lebeg measure is invariant and ergodic. Which other invariant ergodic measures do we know exist for this map? Do you remember which other measures exist?
Invariant measures, for instance, we can consider periodic points, Dirac function for periodic points.
Exactly. So basically, these are the two classes of measures that we know so far for this. So here we have infinitely many periodic points, periodic orbits, and on each of these periodic points we have an invariant measure, which is also ergodic. In fact, okay, so these are ergodic invariant measures. And what I would like to prove today is that there exist many other measures, and in fact we will show that there exists an uncountable family ergodic invariant probability measures mu p, where p is in, let's say, 0, 1, which are non-atomic So non-atomic means that that there is no singleton that has positive measure, right? It's a measure like Lebeg measure. Points have zero measure, right? So they're not Dirac delta on periodic points. They're not combinations of Dirac delta. They don't give any positive measure to any other point, and they're all distinct. So they're all mutually singular. Okay, so mutually singular means they give all positive measures to different sets. So maybe we will write it, I can write it like this. So there exists pairwise disjoint sets AP in I with mu P of AP equals 1. So they live on disjoint sets. That's what mutually singular means, right? So if you have, there is a set that has full measure for this and has zero measure for all other sets, right? For all other measures, right? Because if you take a different value of P, it will give full measure to the, so if you take mu Q, it will give full measure to the set AQ, which is disjoint from AP. So that means that AP must have zero measure with respect to mu Q, right? This is what mutually singular is. So what we want to show, so it's not immediately obvious where these ergodic invariance measures are living here, but there exists all these measures. So this is will be a kind of corollary of what we just did, as we shall see. And it just helps us to construct more ergodic invariant measures in a non-trivial way, right? Because this is kind of what I'm going to introduce is a new tool. The kind of motivation for this is a new tool for constructing, for exhibiting, for showing that there exists other measures that are ergodic and invariant that are not Dirac delta and that are not Lebeg. So how am I going to do this? So we know So first of all, a general, let me make a general comment that if, so you remember that we had, if we have two systems, and we studied the problem of these two systems being topologically conjugate, right? So this conjugacy means that A means you have a point here, so F composed with H equals H composed with G, right? This is the conjugacy relation, okay? And H is a bijection, for example, or it's a topologically conjugate if H is a homeomorphism. Now, if H is a topological conjugacy, then in particular it's also a measurable conjugacy. So if H is a measurable, bimeasurable set, bimeasurable bijection, so if H is a bimeasurable bijection, this means that it takes the sigma algebra here to the sigma algebra there, and vice versa, right?
Professor,
So, sorry?
GH or HG?
Thank you, thank you, thank you. Not everybody is sleeping after all. Thank you, yes.
Also, the left side is HF.
Sorry, okay, we take a point. Sorry, what I mean is HG. Sorry, F, no. So we take a point here, we apply H. Yes, I got it wrong both ways. So I either apply H and then I apply G. So I have G composed with H is the same thing as H composed with F, right?
Yes.
Yes, thank you very much. Yes, you're right. Okay, so it turns out that if you remember the push-forward operator, we can have the space of invariant measures for X and the space of invariant measures for Y, and we can define using H the push-forward operator, where if we take a measure mu, we map it to a measure H star of mu on Y. And this is defined exactly like we defined the push-forward operator when X is equal to Y, right? This is just a little generalization because they don't need to be exactly the same space. So H star of mu of some set A, so we take some set A here. So we have a measure here, right? And we define this push-forward operator, and we define a measure here. And how do we define the measure here? We take a set A, we take its pre-image, and we define it as the image of H minus 1 of A. So we push forward the measure, just like we're doing before, right? So we take the set A, we look here at the pre-image of A, and now here we have the measure mu. We look at this measure, so we define a measure on this space by doing this, right? And then it is easy to see, but it's quite remarkable. I will leave it as an exercise because it's a very simple exercise, is that this measurable conjugacy, remember that I spent quite a lot of time emphasizing how different regularity of conjugacies preserve different amount of structure, right? So topological conjugacy preserves some structure, differentiable conjugacy preserves additional structure. So it turns out that measurable conjugacy preserves both invariance and ergodicity, right? So H star mu is invariant by G, of course invariant, if and only if mu is invariant by F. And similarly, H star of mu is ergodic if and only if mu is ergodic. So this push-forward operator preserves inside here, we have the subspace of invariant measure, the subspace of ergodic measures, and they are mapped exactly to the ergodic and invariant measures here and vice versa. Okay, so how are we going to use this fact for our construction here? Well, remember that we have these topological conjugates, so I'm going to sketch the proof without going to details. You can easily fill them in, and it's in the notes, is the details. So we have shown that any two full branch maps with the same number of branches with the same orientation are topologically conjugate. So we have here topologically conjugacy. So here we have 2x mod 1. And here, I'm going to define I'm going to take a point P, and I'm going to define a full branch piecewise affine map like this. Okay, so these are both the interval 0, 1. This is the point 1/2. So here we have the partition, the two branches are defined on, so let me call this I0P, and this is I1P. I0 and I1 are the two elements. And here we also have I0 and I1 are the two elements. So because of what we just said, so now we're going to use the same argument, the same idea that we just talked about, right? So in this case, Lebeg measure is ergodic and invariant. Right? So that means that almost every point will visit any set of positive measure with a frequency that is asymptotically the measure, the Lebeg measure of that set. So maybe this is the right moment just to make a very brief remark, okay? I did not emphasize that, how in some sense amazing it is that if Lebeg measure is invariant and ergodic for any full branch piecewise affine map, okay? This means that any piecewise affine map, almost every point will visit a particular set with the same frequency, right? If I here take some set A here, then for this map, almost every point will visit A asymptotically with a frequency that converges to the measure of A. If I take this map here with the same set, the same will be true. But notice the dynamics is completely different, right? Points go in completely different place. If I take this point, here it will map to here it will map to somewhere completely. Any piecewise affine map I take, almost every point will converge to A with the asymptotically. So even if it has many branches, even if it has infinitely many branches, right? So this is intriguing because it kind of says that the statistics is almost independent of the map. It is independent of the map, right? It only depends on the fact that Lebeg measure is invariant and ergodic. That is the extraordinary nature of these kind of results. So the map has to be related to Lebeg measure, because Lebeg measure has to be invariant and ergodic. But once you have the invariance and ergodicity, then it gives you this kind of statistical information when you no longer need to know anything about the map. Okay, that was just a small parenthesis. But in particular, now, what we know is that almost every point converges, spends time here, which means that Lebeg almost every point will spend p proportion of time here, right? So here we take a set AP, which is equal to the set of points X, for which the proportion of time for which, wait, let me, okay, wait, without writing something here, let me first, because to write down it would take me a little while. It's all in the notes, but here intuitively the argument is very simple, right? So if we now take the symbolic coding, remember that we can associate a symbolic coding, right? When we constructed this conjugacy, we did this by looking at each point, and you look at a point and you can construct a symbolic coding depending on whether the orbit falls in I0 or in I1, right? So if you now look at the symbolic coding of these points, then you see that the proportion of zeros and ones in this symbolic coding, the proportion of zeros will converge exactly to P. Because every time you fall in I0P, you get a 0 in your symbolic coding. And because Lebeg measures ergodic and invariant, you will fall into I0 exactly proportion P of the times, because P is the length of this interval. Okay? The same thing is true here. In this case, you will spend the symbolic coding will have proportion 1/2 of zeros. Right? Because you will spend, and in this case, the symbolic coding happens to coincide exactly with the base 2 representation, right? Because this is 2x mod 1. So in the case in which we have kx mod 1, 2x mod 1, or 3x mod 1, or 4x mod 1, as we saw just before, the symbolic coding, so the coding that you get by looking at the orbit and seeing whether it falls, in which branch it falls, is exactly the same as the base k representation. If instead of taking 2x mod 1, you take a different map with 2 branches, then you cannot do, then the base 2 representation of the map has no significance, no dynamical significance, but you can still have a symbolic coding between zeros and ones, okay? So if you look at the symbolic coding of these points, almost every point, if you look at now the sequence associated to it, then for almost every point, the proportion of zeros will be P. And in this case, for almost every point in the symbolic coding, which coincides with the base 2 representation, the proportion of zeros will be 1/2, okay, which is just what we proved. Now, the crucial property of this conjugacy, right, and this is what we used for the conjugacy, is that H preserves the symbolic coding. So the way you construct this conjugacy is precisely by matching up all the points that have the same symbolic coding, right? So you take an orbit who has a certain sequence of zeros and ones in this map, and this will map it, this will be mapped exactly by a point that has exactly the same sequence of zeros and ones, okay? So in fact, the set that I wanted to define is maybe, let me define this set here. Okay, maybe I would not define it formally because we've run out of time, but it's in the notes. Okay, so the key point is that here, so we want to use this conjugates to define an invariant measure here, and we define mu p is equal to h star of Lebeg. Right? So here I have Lebeg measure, okay, and using exactly this definition here, this construction here, right? I use Lebeg measure, I take Lebeg measure here, and I apply h star. This is a topological conjugacy, so it's also a measurable conjugacy. So I take Lebeg measure here, and I map it with h star to get a measure mu p, right? And now I want to show two things. I want to show that this mu p are exactly the family of measures that we want. So we want to show, one, that this is non-atomic. And this is very easy, right? Because if we take a single point here, mu p of some single point here is just equal by definition to Lebeg measure of h minus 1 of this single point, right? And this single point, by this conjugacy, can only be either also a single point or at most 2 points, okay? And so this is equal to 0, okay? Because this is essentially, no, this is actually a bijection. So this is actually a single point. Sorry, this is exactly a bijection. So this is a single point, and so this has Lebeg measure 0. And 2 is what did we say, is mutually singular. Singular, and that is because mu p, so if we let, okay, this is the set I wanted to define. We let AP be the set of points x for this map here, such that 1 over n, such that the frequency, so here we can write all the numbers in base 2 representation, just like we did before. So here is 1 over n times exactly what we had before, times from 1 to n, such that xi equals 0. Equals p. So I'm defining inside here the set of all points such that when you look at the base 2 representation, so this is the base 2 representation, just like we did before, it has a proportion p of zeros. Right? So remember what we proved, and I'm almost finished, what we proved before is that if we have, that if we take p equals 1/2, then this set has Lebeg measure 1. Right? Because this is exactly the set of points where the proportion of zeros in the base 2 representation is 1/2. And as we said before, for Lebeg almost every point, we will have equal proportions of each digit. Half zeros, half ones. Okay? Which means that if p is different from 1/2, then this will have Lebeg measure 0 in here. Okay? And also, all these sets are mutually singular, right? Because if you take a point and you look at the base 2 representation and you count the frequency of zeros and it converges to some point 1/3, then it cannot converge also to 1/4, right? So all these sets are all pairwise disjoint, right? And mu p of AP is equal to Lebeg measure of Lebeg measure of h minus 1 of AP. Right? And what is H minus 1 of AP? So AP is all the sets whose base 2 representations has asymptotically p proportion of zeros. So that is exactly corresponds with the symbolic coding of these points. So this is exactly the set of points whose symbolic coding has exactly p proportion of zeros. So when you map it backwards by this conjugacy, it will map here to the set of points whose symbolic coding has exactly p proportion of zeros. But here, this set has full Lebeg measure, right? Because for this particular map, if we take, so this conjugacy, of course, depends on the p we chose here. And for this particular map, the set of points whose symbolic coding has a 0, has proportion p, has full Lebeg measure, right? So the Lebeg measure of this is equal to 1. Okay, and this completes the argument for the proof of this theorem, because we have now defined, basically, you can change p, right? And for each different p, unless p is a half, when p is a half, h is the identity, but for every other value of p, you will get this conjugacy hp, and this conjugacy will send this full Lebeg measure set of points, which are the ones, typical points with respect to Lebeg measure here, and they will spend p proportion of time in here. It will send it exactly to the points for which the frequency of zeros is p, right? And that is a set of 0 Lebeg measure in here, and therefore this measure mu p is living on this set that has 0 Lebeg measure set, but it's still a uncountable set. In fact, it's an uncountable set here. It is invariant by the dynamics because it is defined by an asymptotic property, and so there's this measure here which is invariant and ergodic and lives on this set AP. Yeah. Okay, and this gives us a countable family of ergodic, invariant, mutually singular sets which are non-atomic, they're not Lebeg, they live on sets of 0 measure, but they're uncountable sets of 0 measure. So it is an extremely rich world of invariant ergodic measures. This was the purpose of this example here. Okay, so that's it for today. I'm sorry we went off a little bit late. I'll see you next week, hopefully here. I think that would be much better if we're all in the class. Okay, bye everybody.
Thank you. Bye.
Bye,
Bye.
Professor. Thank you.
Thank you.